Okay, so we've talked about inelastic collisions when energy is not conserved. So as you can imagine, an elastic collision is one in which energy is conserved. Okay, but I have another name for elastic collisions. Basically, elastic collisions are algebra hell. Okay, there's really no way to get around, just having some nasty algebra to work through when you're doing problems that involve elastic collisions, because an elastic collision problem is going to go something like this. We're going to have some mass, we'll call it mass 1, moving with the velocity v, and then we'll have some other mass at rest, we'll call it mass 2. Then they're going to collide. After the collision, then we'll have mass 1 is moving to the right with velocity v1, and mass 2 is moving to the right at velocity v2. Now it could be that v1 bounces back the other way, and we would find that out because if we get a final answer that has a v1 is negative, we know it's moving to the left. But since we've defined the right as our positive direction, we draw both v1 and v2 to be positive to the right. Okay, so how would you go about solving a problem like this? So basically the problem would be given the mass of one, so we'll be given m1 and we'll be given m2, okay, and we need to find v1 and v2, their final velocities after the collision. Okay, so how do we do that? Well, what we do is we have two unknowns now, so it means we're going to need two equations. So the first equation that we have is that m1 v1 m1 v, right? So mass 1 times the velocity, because this is the initial momentum, it's all in the first mass, is equal to the momentum of the first mass after the collision plus the momentum of the second mass after the collision. Okay, and then we can solve this, and so we'll say that this is saying that v is equal to v1 plus alpha v2, where now we define alpha is equal to m2 divided by m1. Okay, so in other words, we divide everything by m1, and we could come up with that. Okay, then the next thing that we do is, now because kinetic energy is conserved, then we can say 1/2 m1 v squared is equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared, right? Kinetic energy is conserved, so this is our initial kinetic energy, this is our final kinetic energy. The collision's elastic, which means that's completely conserved. So again, we divide by m1 and we multiply by 2. So now this gives us a new equation that says that v squared is equal to v1 squared plus alpha v2 squared. Okay, so from here, now we can say, looking back at our first equation now, so if we look back up here, we can rewrite this and say that v2 is equal to v minus v1 divided by alpha. So v2 squared is equal to v minus v1 squared divided by alpha squared. Okay. However, if we look back at our energy equation that we got, we also see that v2 squared is equal to v squared minus v1 squared over alpha. So now we can set this equation and this equation equal to one another. So as I said, this was simple enough to set up. We use conservation of momentum, we use conservation of energy, but now we really do find ourselves in kind of this algebra hell of starting to have to solve these equations. And so we do this, and so we multiply by alpha, and so we see that on the so that we can rewrite this as v squared plus v1 squared minus 2 v1v, so that's this term, okay? And if we multiply by alpha squared, then we can say that this is equal to alpha times v squared minus v1 squared, okay? And so now we move these over to the other side, and so we see that this is going to tell us that that v1 squared times alpha plus 1 minus 2 v1v plus v squared times 1 minus alpha is equal to 0. Okay, and now we have to remember our quadratic formula. So in case you've forgotten that, I don't think we've had to use that yet this semester. So remember, if we have something that's ax squared plus bx plus c, then the solution to this is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So we just plug that into this equation. And so we see that this is going to tell us that v1 is equal to 2v plus or minus the square root of 4v squared minus 4 times alpha plus 1 times 1 minus alpha v squared, and that's all divided by 2 times alpha plus 1. Okay, and then we do some algebra. Again, I think there's no point in me continuing to work through the algebra on this, especially because this is actually done exactly in your book. But so we see that this is equal to v times 1 plus or minus alpha divided by 1 plus alpha. Okay, so again, we have this plus or minus here because we have a quadratic equation. There's two solutions. But we notice that if we take the plus alpha, then these just cancel out. We just get the speed v. And so this would be what happened in the case where there was no collision, right? There's nothing there, so the first particle emerges with the speed v. So that doesn't really make sense. So we see that the only solution that makes sense is that v1 is equal to v times 1 minus alpha over 1 plus alpha. Okay, so just to make one final comment about this solution that we get, notice that this tells us if alpha is mass 2 over mass 1. So if alpha is greater than 1, which means mass 2 is greater than mass 1, we see that means that v1 is going to move to the left, because this is going to become a negative term. So if mass 2 is greater than mass 1, then our final velocity v1 is going to be to the left. If, however, mass 1 is greater than mass 2, then this is going to be positive, and so it's going to be moving to the right. And then we have the special case where mass 1 equals mass 2. In that case, alpha is just equal to 1, so v1 is 0. So this gives us a result that we've probably known that we've seen before, which is that if both masses have the same mass, then after the collision, one of them is going to stop and the other one's going to move with the initial speed that the first one had. So that's all there really is to inelastic collisions. Note that the most important steps were really drawing this equation, conservation of momentum, and this equation, conservation of energy. Once we have those two things, from there it's just algebra. So when you're working on a problem like this, your biggest focus should just be on setting it up right. And then if you mess up the algebra somewhere along the way, you're probably likely to pass the exam. You'll just lose, maybe 1 point for making an algebraic mistake, because it's very easy to do when you get problems like this that start to get fairly long.